Okay, hello. So this is it. We're going to finally start doing quantum computing. You're all set up for quantum information theory, qubits, you know how it all works. And now for the next part of the course, we're going to talk about some quantum computing, quantum algorithms. But actually, before we get into the basics of quantum computing, we're just going to start a teeny tiny bit with like the basics of classical computing. And in quantum computing, it's very convenient to talk about your quantum computer and the circuit model. We've been doing this implicitly already with qubits and like these little quantum gates. And therefore, it's a good point of comparison to compare yourself against the classical circuits model for computation. Okay, so in the classical circuit model for computation, you compute Boolean functions or you mappings from strings to strings with and or not gate circuits. Okay, so typically we imagine we have some n-bit input, and then these go into wires and or not gates, and out comes one or more output wires, which I've denoted here y1 through ym. And most often you focus on the m equals 1 case for simplicity, functions that just output, computing things that just output 1 bit. You can think of this as like m separate circuits, one for each output bit. But you can also have more than one output bit. So in general, if you have a classical circuit C that looks like this, it computes some Boolean function f that maps n-bit strings to m-bit strings. Okay, so maybe like this is like the binary representation of a number, and you want to output 0 or 1 depending on whether it's prime or not. So you might build a classical circuit that can do that. And as I mentioned in lecture 1 in this course, we're going to focus a lot on the efficiency. So given some like task, some desired function f that you want to actually compute, the most basic question in terms of efficiency that you'll ask is, well, how can I compute it using the fewest number of gates? So in particular, not just that, but like how does this scale with n? These are the two main questions we'll focus on. Okay, again, to take, for example, the problem of deciding if a number written in binary is prime or not, you want to solve this for differing values of n and want to understand how many circuits does how many gates does your circuit need as n grows? And you can focus on other resources too, besides just the number of gates. But the number of gates is like the main measure and the most simple thing and most important thing. So that's what we'll just focus on for simplicity. And in some sense, the number of gates in a classical circuit should somehow correspond to, or does roughly correspond to, the number of time steps that like an algorithm takes. So for example, if you have a circuit, then essentially to evaluate it takes no more time or steps than the number of gates, because you can just go through it and it takes you a fixed number of steps or time to evaluate each gate. And in some sense, the reverse is also true. So actually, sometimes you can have a circuit that can finish in much less time than the number of gates if like a lot of parallelization is possible. Like here, you can run these two and not gates at different times or at the same time, because they don't depend on each other. And this parallelization is important to work with or to think about in practice, but we'll mostly just keep it simple and measure efficiency in terms of number of gates. Now actually, when you learn about the basics of theoretical computer science and time complexity, you're probably more used to thinking about this in terms of like algorithms and like code rather than like actual circuits. So you might think, oh, I should actually, how would I implement a function or some code that computes this function? So if it was Python, you might have something like this, has some like lines of code, and then finally returns the answer. Or if you're really into computer science theory, you might have like the Turing machine model in your head where there's some like tape or something with like X on it. And you count like the number of steps that this thing takes. But I just want to briefly tell you that like the running time of algorithms is really quite comparable to the number of gates in the circuit model. So let me just state one fact along these lines. This is all of which all of this is to like justify to you like why it's okay to focus on this circuit model of computing. So this is a theorem that you can prove. I mean, given some Python code, or it could be any programming language that computes a function f in some t time steps on length n inputs, then it's not hard to, you can like easily produce an and or not circuit, computing f as well on n-bit inputs using a number of gates, which is basically t. So if you are careful, maybe it's t log t, and then there's a constant that depends on the programming language. Okay, so if you want to do it in Java or Turing machine, you might have a different constant here. And this log t is some small amount too. In practice, that's at most whatever, 50 or 100. So the main thing is that the number of gates you need to bake into hardware, like any software algorithm, is basically like the running time of the algorithm. Okay, so if you're used to the fact that I can write a Python program that will sort n numbers in n log n time, then you can also build a circuit, like and or not circuit, that sorts n numbers in something like n log n gates. Yeah?
Wasn't there quadratic slowdown, or am I thinking of something else?
The naive way to prove it gives a quadratic slowdown, but if you're sharp, you can prove this. Yeah?
This might be a silly question, but is it possible, programming languages like Python or whatever, for it to tell you how many NAND gates were needed to complete, a running of the code?
Well, they usually don't get down to that level. Although, I mean, usually on a normal computer, all your Python or high-level language gets compiled down to some assembly language at the end, which is pretty close to a circuit in the sense that it's real simple, except that it has jumps and stuff, which circuits don't have. So no, I mean, you could write something that really would do it. But I guess nobody typically does that. Okay. Conversely, it's also possible to define quantum Turing machines if you want to do that level of comparison. But it's very annoying, so it's much nicer to just think about circuits. Okay, so now that we're going to think about all computation classically and also quantumly in this circuit model, then let me just remind you of a couple of facts related to efficiency. So the famous Claude Shannon, in his master's thesis, the most famous master's thesis in computer science, he proved the following theorems. This was in 1937. First of all, every function, let's focus, for example, just on functions with one output bit, can be computed by some circuit. And the number of gates needed is at most 2 to the n. Okay, and in fact, if you're super smart, which Shannon was, you can even get this to be divided by n. That's not a very big savings, though. So this is good and bad. I mean, it's good in it says that, okay, circuits can compute anything, but 2 to the n is very bad, right? I mean, once n is a few hundred, 2 to the n is some unphysically large amount that you could never build in the physical universe. So this would be infeasible if you had to use it. And in fact, he also proved that you do need this many gates for almost all Boolean functions. So he also proved that almost all, in a technical sense, f's like this need at least 2 to the n over n gates. I mean, for almost all Boolean functions, the smallest circuit has this exponentially many gates. So again, that's on one hand bad, but there's nothing you can do. That's the truth of the matter. And luckily, we're not interested in computing every possible function or a random function. We have some interesting functions that we care about, like multiplying numbers, checking if numbers prime, finding the shortest path in a graph. I mean, the normal things we solve by algorithms. Good. And sometimes, not always, but sometimes these problems that we actually care to compute, like the ones I've just mentioned, can be solved with much more efficiently with like a reasonable number of gates, like a number of gates that grows like a polynomial in the input size, like proportional to n or n squared or n cubed. And these are like the physically plausible circuits or algorithms. Okay, so that's the quick summary of classical computing and efficiency, and now we're going to talk about the same story but in the quantum setting. First, though, I have to briefly mention also probabilistic computing. Since quantum computers, quantum circuits have measurement gates that are inherently probabilistic, it's most fair to compare yourself not to just good old deterministic computation, but also probabilistic computation, which it's eminently reasonable in the real world to have probabilistic computation. So this is a brief aside. Well, if you want to augment this, if you decide this is your model for classical computation and or not circuits, and you want to augment it with probability or randomized computing, it's easy. You just add one more kind of gate. Maybe on the homework it's called a flip gate, coin flipping gate. And this is a gate that has no inputs, but it does have one output wire. Okay, and just by definition, it outputs 0 or 1 with probability half each. Okay, so if you want to have randomized computing, then just throw these flip gates into your model. And now, as we discussed before, but as I'll remind you one more time, you need to think a little bit carefully about what it means for a randomized computation, a probabilistic computation, to successfully compute something, to successfully compute a Boolean function f. And you explored all these details on homework 1 and problem 5 with the 0-sided error and the 1-sided error and the 2-sided error and amplifying your success probability by repetition. So there's more to it than what I'm about to say here, but the simplest thing to say is the following. Probabilistic computation, let's say a probabilistic circuit will say, successfully computes a Boolean function f if, okay, for all inputs, there's no randomization in the input. It outputs the right answer with high probability. So the probability that that c of x, what the circuit outputs, differs from what the true output should be, f of x. And this probability is with just respect to the coin flip gates. This should be small. And what you actually define small to be doesn't matter too much. We can say 1%. As you saw in the homework, if it's 40% or if it's 0.01%, doesn't make too much of a difference. If you have an algorithm with 40% error, you repeat it a few times, you can get the error down lower. Finally, the reason I call this a bit of an aside is we talked about probabilistic computation a lot in lecture 2, if you can remember that far back. And one of the things I tried to convince you back then is that while probabilistic computation does seem like it may help you speed up computing some problems a little bit, whereby a little bit I mean maybe it can take one algorithm that has polynomially many gates or polynomial much time and change it to a smaller polynomial, we strongly believe it doesn't give you any exponential speedups for any problems. Okay, so we strongly believe that just for these problems like compute a Boolean function, there's no such Boolean function that can be computed with a physical, plausible, polynomial number of steps by a probabilistic computer that can also be done with a physical, plausible, polynomial of steps on a deterministic computer. Okay. Any questions so far? All right, so now really we're going to talk about quantum computing. Okay, so we already kind of been implicitly talking about quantum circuits so far, They've just tended to be like really simple circuits with like, 2 photons or 2 qubits, and we did like some funny little magic tricks with them. But now we're going to talk, seriously about, having n like 100 or 1,000 or 10,000 bits as an input, and like having that many photons, or however we're going to store the qubits, and putting them through a real roller coaster of quantum gates to try and get a classical outcome. So the picture of a quantum circuit, or quantum computer, if you will, looks similar to this. Okay, we're not going to use these gates, but we are going to have, n input bits. And I'll put the little ket symbols around them because we imagine that, the way it works is if you want to have your quantum computer solve the problem or compute a function f on a string like 101, then, you prepare a qubit in the state ket 1, and the second qubit in the state ket 0, and the third qubit in the state ket 1, and like those will be the qubits, the photons you plug in. Okay, so the inputs are always, unentangled. We imagine, zeros or ones. Okay, and then, these are, real photons or whatever. They have their own identity. So like, unlike actually in the classical case, like these wires, well, first of all, they're not really wires, and they also don't kind of diminish. These are actual, like, let's say photons that like last their own lifetime and potentially go through gates. And we put them through, quantum gates, like C0, that's a classic, or like Hadamard, that's another classic, or maybe these like rotation gates, like 45-degree rotation. These are all some classic gates. Some swap gates or whatever. And then again, we're going to have outputs. So now, at the end, we'll still have, n qubits. And we might measure some or all of them. So I'll draw these measurement gates, if you will. And we'll assume that these are, measuring in the standard 0-1 basis. Okay, and these read out classical information. Maybe in this picture I've measured 3 of them, y1, y2, y3. That's if m is 3 and I'm trying to compute a 3-bit function. Okay, so you can measure some or all of them. Okay, and then we say that a quantum circuit computes a Boolean function like this if exactly this. Okay? Same thing, except that this, instead of the probability being over the flips, it's over the measurements. Okay, so we want it to be the case, if this is supposed to be computing a function from n bits to 3 bits, that for every one of the 2 to the n input Boolean strings, if you encode your qubits like this, run them through this circuit, measure the first 3 qubits, then with high probability you see the correct answer. Yep?
So why would we not measure all the qubits at the end? Because when we treat this, we would always end up just treating it as if we had measured those ones we didn't measure.
Yeah, it doesn't matter. You can. It's not going to change the analysis or anything. Yeah, you can imagine that like all of them get measured without loss of generality. And you just, if you only plan on having 3 output bits, then just ignore the other n minus 3 measurements. The most common thing you'll actually eventually see is, because we're most normally, for simplicity, talking about computing 1-bit functions, is actually just you measure the first qubit. But it doesn't matter for analysis purposes if you measure them all or not. Actually, on that subject, let me say a couple of things. First of all, the way I've drawn this picture has like all the unitary gates in the middle and all the measurements at the end. Now, in the physical world, there's nothing stopping you from like having some measurement gates in the middle and like, I don't know, doing future gates based on their outcome. But as you are currently seeing on the homework, there is something called the principle of deferred measurement, which is basically a simple trick for taking any potential quantum circuit with like measurement gates in the middle and like moving them to the end and having the 2 circuits, the pre-move and the post-move circuit, behave identically. Okay, so I won't do that in the lecture, but you're doing it in the homework, and what it means is like it's without loss of generality in your quantum computers to have all the measurement gates just at the end. Okay, and that's actually good. We like it. It's simplest this way.
So we can, without loss of generality, assume that they're at the end, but can we assume that there's just one per line? Or could there be like a bunch?
Well, what picture do you mean? I mean, there's no point in having like a second measurement gate here because you've already measured, so like nothing's going to change if you measure it again.
Maybe you do it on a different basis for some purpose.
Well, I mean, once you measure it, then it becomes like classical information, and you'll be able to exactly know what will happen in every other subsequent measurement. You can have it measuring in a different basis, that's fine. Although, again, like if you want to measure it in like the sine basis, then instead you can like first Hadamard it and then measure it in the standard basis. Yeah?
What if you do other stuff to it? Like what if you measure y1 and then you C naught y2 with y1 with y2 as a control bit? Now you've got something that's a different state.
Yeah, so that's taken care of a little bit in your homework in the sense that like, yeah, I mean, for everything that you might do with like a measurement internally or like not right at the end, and you do have to introduce like an extra qubit to your story in order to pull this trick off, but you can convert it to an equivalent circuit where the measurements are at the end. It's even smaller without loss of generality. I mean, I drew the picture here where like the first 3 qubits were the output that you cared about. On one hand, really, maybe like the way you designed your circuit, like you care about qubits 2, 3, and n. But without loss of generality, you can put like some swap gates in here to move the qubits that you really care about the measurement to the beginning. So we'll also always assume that like if you care about m output bits, it's like the first m. It's just a small comment. Okay. And I should also add, like, when you set up your circuit this way, it's kind of funny because, this is your input state, and this whole business here is one like massive unitary transformation on 2 n-dimensional space. But the measure of efficiency is like how many like little like 1 and 2 qubit gates, like C naughts and 1 qubit gates you need to build up this one massive unitary. Just in the same way with like and or not gates. I mean, like the big circuit, you can think of it as like one gigantic gate that has n inputs, but that's not fair, right? You measure it in terms of like how many little and or not gates you need to build it. Okay, so that's the model of quantum computing. There we have it. And now we're going to ask, some important questions. So, well, the biggest question on everybody's mind is, are there some Boolean functions f which quantum computers or circuits can compute much more efficiently than classical ones? And the answer to this question is with a yeah, we think so. I mean, factoring being the prime example. I say we think so because we know, and we'll see in a half dozen lectures, that there's a quantum circuit that computes solves the factorization problem pretty efficiently, the reasonable number of gates, something like n squared gates for n-bit numbers. And we don't think there's any such circuit classically. Yep.
Yeah, that's a question about the previous quantum circuits.
Yeah.
So is it possible to compute any function using the small like C naught and rotation gates?
Great question. So you're anticipating exactly some things I'm going to say now. Good. So that's the first question. But actually, we're going to talk about this over the next few lectures. But today, we're mainly going to talk about question 2, which is actually literally the converse question. Namely, are there any Boolean functions which classical circuits can compute much more efficiently than quantum circuits? It's not really obvious that this model of computation is at least as powerful as classical circuits. As we'll see in a second, like if I was like, okay, compute the and of 2 bits, it's not completely obvious how to do that in the quantum case. In fact, we'll have to think about it a little bit. So yeah, the reverse question is, I mean, have we defined a model that's potentially even weaker in some ways than classical computing? Well, the answer is going to be no, but that's what we'll talk about today. And then what we're going to also talk about somewhat soon, probably next lecture, is an important problem, a bit of a side problem, but it's important to think about, does the exact quantum gate set matter? For example, in classical, computing, electrical engineering, I assume you get like the 2-input AND gate, the 2-input OR gate, and the NOT gate. Why? I don't know, it's kind of traditional, honestly. But you've probably seen before that it doesn't really matter as long as you put in like enough gates. You can simulate like an XOR gate on 2 bits with AND or NOT gates. So it doesn't really matter to efficiency exactly what gate set you choose. So you just say AND or and NOT for simplicity. Basically, the same thing is true in the quantum case. But there's a few fine details that it's worth like talking about, and so we'll talk about those probably next lecture. But another quick summary is like, if you want to go home and start programming quantum computers, what you know now, or what I've told you already is okay, namely C0, and basically any 1-qubit gate. That's sufficient. That's universal for all quantum computation. Okay, good. Any more questions? Okay, so good. So let's talk about this exact question now for basically the rest of class, which is, can we even show that like quantum computers are at least as powerful as classical computers? Okay, and this is actually kind of a fun topic. The answer is yes, and I'll show you how you can simulate any AND or NOT circuit with like a quantum circuit, and it's just kind of entertaining. So as I said, it's actually in some sense not obvious at first, and in some sense it's not even quite true at all that a quantum computer can compute even like a single AND gate. Okay, and why is that? In fact, why can a quantum computer not do that literally directly? Well, okay, what are the things that a quantum computer can do? What is the allowable gates in a quantum computer? We know that all these gates are unitary. They're all unitary transformations. Unitary matrices. And to remind you, what is that? These are linear transformations U that satisfy this equation. U dagger equals the identity. And in particular, that means that U dagger, the conjugate transpose, is U inverse, which in particular means U inverse exists. So U is invertible. Or one might say, especially in today's lecture, reversible. So all these gates here have an inverse or can be reversed. In other words, if you know the exact state that came out, then you know the exact state that came in. Or you can infer the exact state that came in. In fact, kind of amusingly, this is not essential, but most of the gates that we talk about have the even stronger property that they're their own inverse. Okay, so like Hadamard is its own inverse. If you Hadamard a qubit and then you Hadamard it again, that's the same as doing nothing. Same with C0. I guess these rotations are not their own inverses, right? I mean, rotation by 45 degrees, its inverse is rotation by negative 45 degrees. Okay. But like the NOT gate, C0, the Z gate, they're all their own inverse. But, this classical AND gate is not reversible. I mean, look, if you put in 0, 0, or you put in 0, 1, or you put in 1, 0, all three of these give out 0. So it's not reversible. If I just tell you the output, you cannot infer what the input was. Somehow you lose information when you put bits through an AND gate, potentially. Okay, so somehow an AND gate, it erases information. And that's not possible with quantum gates. So yeah, that's why you might think that's why it's not completely obvious that quantum circuits are at least as powerful as classical ones. Same problem with an OR gate. I'll just mention that a NOT gate is reversible. I mean, 0 maps to 1 and 1 maps to 0, so that's fine. You can invert that. And that's sort of consistent because actually NOT is like a perfectly valid quantum gate we've seen before. So in fact, this topic of reversible computation was something that was studied a lot by physicists in like the 1960s and 1970s, independent of quantum and quantum computing. They were thinking about it completely separately. Its key early figure was a guy called Ralph Landauer, who was a physicist who worked at IBM. And they were building supercomputers and things. And one thing they were really interested in the 60s and 70s was trying to understand like what is the minimal amount of energy, like physical energy, needed to do one step in a computation. And this guy Landauer sort of figured out that like it's not really steps per se that require energy, but it's this, erasing information. Now, I have to say, like, I don't know anything about physics, so I'm not exactly sure what the words I'm about to say mean, but I'm told they're meaningful, and hopefully you'll get the gist, like I've got the gist. So I guess the classical laws of physics are time reversible. That is, like they should operate the same if time is reversed. And in principle, a reversible computation like a NOT gate can be done in like a closed physical system in such a way that there's no energy loss or gain, I guess. I mean, because of its reversible nature. Whereas by contrast, like a non-reversible operation like AND somehow loses information or erases information, and so like entropy is lost. And therefore, by the second law of thermodynamics, like it has to go somewhere. And therefore, like if you have an AND gate implemented somehow physically, it cannot be a closed system. And like heat, for example, somehow has to escape if you really implement an AND gate. And so you can imagine, therefore, like why the physicists were interested. I mean, they were like, well, I mean, if we could somehow make all gates or operations in our classical computers reversible, theoretically, they could be done with like no energy loss or heat dissipation, and that would be great for physically building them. Or at least, in practice, maybe it would allow them to greatly minimize the like heat dissipation required by the computation. And then I guess it turned out in the 70s and 80s, people started like building computers, and it turned out like this heat dissipation thing was not really a big problem. And so they're like, all right, well, that reversible computation stuff we thought about was kind of fun, but didn't seem to play a big practical role in those days. But it turns out, A, it's highly relevant for quantum computing, because in quantum computing, all the unitary gates are reversible. And I'm told that like these days, now that they're trying to make the chips like so efficient and like microscopic and atomic level, that like they might actually start to care again about this reversibility and like minimizing the amount of energy you need. Any questions or comments from those who know more than me? Yeah?
I just have a question to make sure I'm getting the direction correct.
Okay.
So when you erase information, that costs energy. So if you reverse it in a time perspective, then you get both information and energy back.
Well, I mean, logically, you cannot reverse it. You cannot reverse logically an AND gate.
Right.
But I guess like the fact that it's irreversible implies that like any physical way of implementing it must cause some energy to escape from your closed system, your potential implementation of this circuit. Yep.
Is this related to uncomputing?
We'll get to these things, yeah. Yeah.
So would it be the case that if you were to like always output x2 and x1 and x2, then you could get some partial information back. Like you came to a complete reversal, but you can at least do some reversals, right? So if you were to do something like that, would that lead you to losing less energy?
Yeah, and in fact, we'll see that's kind of going to be how it's going to work. So the suggestion was like imagine like a souped up AND gate that outputted not just AND, like x1 and x2, but like it also outputted x1. We'll see that's like closer to being reversible. Like probably now there's like more cases where you could infer what the input was based on the output. I think like now you're only stuck if you see like 0, 0, you're not sure. You know this was 0, you're not sure if this was 0 or 1. probably that would mean like this needs to dissipate less heat. In fact, we're going to see like a trick where you'll be able to fully reverse everything. That's kind of similar to this idea.
Well, yeah, if you just output x1, x2, and x1, x2, like 3 bits.
Yeah, I guess some aspect of the definition of reversible is also that like this number of input bits is the same as the number of output bits. But actually, we're also going to sort of solve this problem by like imagining like extra bits are going to be plugged into our computation. So, okay, let me also just mention some key names in reversible computing besides Landauer. It's this guy Yves Le Cerf, who was like a French-Syrian ethnologist who, for some reason, which I don't know, like figured out how to build a reversible Turing machine in 1961.
Wait, ethnologist?
Ethnologist, yeah.
What's that?
Studies like human ethnic groups.
Oh.
Yeah. Fredkin, Toffoli, Feynman, our old friend Charles Bennett, Huffman, the Huffman encoding guy, Lorenz. These were the people who were working in like the 60s, 70s, 80s on reversible computing. Okay, so we're going to do it. And here is going to be the workhorse. It's actually a new gate that I'm going to invent for you, a quantum gate or a reversible classical gate. Actually, you've seen it before, so it's not so new. It's a C-swap, the controlled swap gate. I think that was on your homework 3, building a simulator of a quantum computer. This is a controlled swap gate, or also called the Fredkin gate. And we're going to draw it like this. And it's a 3-input, 3-output gate. And first we'll describe it just as like a classical gate, but then since it's a reversible one, a permutation, we'll observe that it can also be a quantum gate. So what does it do? Just to remind you, it's one of these controlled things. So like it always just passes through x1. And then here, it's either going to be x2, x3, or the swap, x3, x2, depending on whether x1 was 1 or 0. Okay, so if x1 is 1, it swaps these 2 bits. Otherwise, it leaves them. And this is like gives a permutation on the 8 possible inputs. Precisely because well, it's not hard to see that you can reverse this. In fact, it's not hard to see that this gate is, again, by luck or chance, its own inverse. If you do the C-swap twice in a row, it's the same as doing nothing. Because certainly the first bit never changes. And then actually, if the first bit is 0, you don't swap twice. And if the first bit is 1, you swap twice. Okay, so this thing is its own inverse. Which means that if you think about it as a map on these 8, 3-bit or qubit basis vectors, it's just a permutation. And as we saw when we discussed, quantum gates and unitaries, every permutation matrix is unitary. And therefore, this is a legal quantum gate as well. That is, it's possible to physically affect this operation even on qubits. And we're just going to assume that you in your lab can build this 3-qubit gadget, this controlled swap. I guess in practice it's actually pretty hard. But in the notes, I'll write down how you can build a C-swap gate out of 4 C-naught gates and some controlled square root of naught gates. So you can build it from some 2-qubit gates, some 3 of those. But we're going to stay at a theoretical level here, so we'll just assume that you can have an ample supply of C-swap gates in your quantum lab. Okay? It's only 3 qubits, so it's not like we're assuming everything here. Yep.
So from what I'm seeing, the purpose of the swap gate is to swap bits because our gates are only acting adjacent qubits, right? Or the block lines next, x1 next 2 or x2 next 3. We can't have a 2-qubit gate that works on x1 next 3.
Okay. So in this class, and in theory, we're going to be pretty flexible about that too. Like I may just like randomly say, oh, you can have this, you can have the control bit be this one, and you can apply it to swapping. It's hard to draw, but like somehow swapping, I don't know, the first and third qubit.
Okay.
And in this class, I'll just be like, that's fine, you can do that. Now, okay, in real life, you probably have to actually like do swap gates on adjacent qubits to like get them all together, because they all have to go into some like physical apparatus that accepts 3 qubits, does a C swap and outputs them. And then maybe you have to like do swap gates to move them back to where they were. But we're not going to get very stressed about that in this class, because it doesn't make a big difference to efficiency. Yep.
Okay, I was just gonna ask, well, I guess why does it not? Because like if you have to swap all the way down, that could take n steps.
That's true. I mean, if you really were not careful, then it could be that for every n qubit computation, having to do all these swaps so many times might like blow up your computation time by a factor of n. For like the very theoretical types, we'll be like, well, if you're used to be using like n cubed gates, and now you're using n to the 4th gates, well, this is still a polynomial. And maybe that's okay if, let's say for classical computers, right, if n is 1,000, then this is 1,000,000, this is 1,000,000,000. It's worse, but like it's not, you've not entered the land of like, astronomical, like more time steps than the age of the universe. In practice, you should care about this a little. I think you'll find that like all the algorithms we actually do can be arranged such that, all these swap gates and C-NOT gates and so forth are on like neighboring qubits. I mean, these are things that you have to care about in practice. I mean, really in practice, I think when they're trying to build quantum computers, their actual qubits are arranged not on a line, but on a 2D grid. And then like you have the ability to swap maybe, neighboring things on the grid, which gives you more flexibility. If you have to swap something from very far away, it's only like square root n swaps instead of n swaps. These are important questions in practice, but we'll mostly ignore them in this class. Okay, so once we grant ourselves the ability to do this C swap gate, we'll see that you can simulate AND and OR and NOT gates. And so what I'm going to show you now is like how to take a classical circuit and re-implement it with reversible classical gates, mainly this C swap gate and maybe also NOTs. And then that will prove that quantum computers can simulate classical computers, because you'll have a quantum circuit that like only uses these kind of permutation gates, and so like it'll actually basically be a classical reversible circuit, but in particular it proves that quantum computers can simulate classical ones. So let's do it. I mean, in other words, in this quantum computer, like the state of the qubits at all times will be not a superposition. It'll have its 100% of its amplitude on, things that look like unentangled zeros and ones. But that's fine. Okay, good. So just imagine classically now that you have an AND gate, and whatever reason you want to like convert it to something reversible. Well, I'll just give away the answer here. Let's see, we have x1, x2, and the trick will just be say like, just bring in a new qubit or bit that's set to 0, and then do this C swap. And well, let's look what happens. Of course, this is x1. We don't really care about that, but well, let's check out what's coming out right here. It's not drawn very straight. This is supposed to be this guy. Well, you see, if x1 is 0, that means you don't swap, which means this 0 will just go through. So far, so good, right? If x1 is 0, the output is definitely 0. And what if x1 is 1? That means you will do a swap. And so the last output bit will be whatever x2 is, which is 1 if x2 is 1 and 0 if x2 is 0. So it works, right? This is x1 and x2. So nice. And this is something else. but we basically don't care. Okay, so it's sort of obligated to be there, so that we have this reversibility property. But we're just like, that's fine. We computed some bit that we don't care about. And that's it. So just some terminology. This thing is called an ancilla. And we'll get used to this word because it gets said a lot in quantum computing and reversible computing. Basically just means it's like some bit that you brought in to facilitate your computation. It's like not part of the input per se. It's just like, I need some catalyst bit to like make this thing work. Okay, and usually it's set to 0. And this kind of thing, and actually, to be honest, this thing, we didn't really want it either. These bits are called garbage bits. A little bit funny, but that's what they're called. And that's it. So yeah, you can get the AND of 2 bits using a C-swap and an ancilla. And okay, what about an OR? Well, one thing you know is, first of all, NOT is no problem. You might say, what about a NOT gate? Well, NOT is already reversible. So we already have like NOT gates, so we can just have NOT gates, that's fine. And then if you're like a teeny bit sophisticated, you know, oh, like you can build an OR gate out of like some NOTs and some AND gates using De Morgan's laws. So that's one solution. Or just whatever, I'll show you how it's equally easy to do OR gates with these C-swaps as well, so I'll show you that just for fun. So you have x1 and x2, and this time you make your ancilla 1, and then you do this. And of course x1 comes through here, and now the key is to look at this output, and let's see. If x1 is, okay, well, I'm claiming that it's x1 or x2. So if x1 is 1, then you definitely swap, and this 1 you stuck in here goes up here and comes out. So that's good. If x1 is 1, you output 1. And if x1 is 0, you still output 1 if x2 is 1, because you don't swap. Well, the only way you get a 0 output is if they're both 0. Yeah, then you don't swap, and this 0 just passes through. Okay, so this is garbage. This is also garbage if you want. And this is an ancilla. Actually, it's traditional to make all the ancilla bits 0. You don't have to, because these are things that really you're just like, well, I'm going to have to do an AND, so I'll like cook up a new qubit that's 0 or 1. But you can cook it up to be 0 or 1 if you want. But it's traditional to make all the ancilla 0. So fine, you can just do this. Put a NOT gate and a 0 ancilla. So it might look like we're done. We did it. We simulated every classical gate that we needed, and or NOT with this C-swap and maybe NOTs. So we've computed everything reversibly. Actually, though, there's one thing that we missed. It's a little bit subtle, but it's important. You see, if you go back to classical circuits, circuit diagrams, you actually always allow yourself to do this. Put these into like different gates. Okay, so you allow these like forks, or this is called sometimes in circuit theory, fan-outs. You're allowed the gates to have like multiple fan-outs. And actually, physically, something has to be happening here, right? Like there has to be some kind of physical gadget in your circuit to allow like this wire to branch out its value twice or more times. But yeah, we have to handle that. So I like to think about this as like an actual gate that we're trying to simulate classically, called a fan-out gate, or sometimes I call it a duplication gate. And its classical definition is just this. If you put x1 in, then x1 and x1 come out. Okay, we have to actually handle this case too. But luckily we can. Okay, so here's the picture. We're going to draw another one of these things. The good old C-swap. And here's the trick. This is what we want to duplicate. Put a 0 in here and a 1 in here. Okay, or if you want all your ancillas to be zeros, then you can do this trick again. And what comes out? Well, by definition, x1 comes out here. And I claim that x1 also comes out here. Because, well, if x1 is 0, that means you don't swap, so this 0 just passes through. That's good. If x1 is 1, then you do swap, so this 1 swaps up to here, and you get 1, which is good. In fact, incidentally, yeah, this garbage bit gives you not of x1. So actually, this is just like an amusing aside. You can even simulate knots with C-swap gates, which means that you can use exclusively C-swap gates, like no other gate except C-swap gates, if you allow yourself ancillas that are both 0 and 1. So for, this is just about classical computing. I mean, you can make a circuit, classical one, that does anything you want with just these C-swap gates and ancillas. But, we're not going to get super excited about that. We're happy to also have NOT gates and C-NOT gates. Okay, so great. So let me summarize what we've shown. Okay, so what we've shown here is a theorem. It's from like the 70s, I guess. Any classical circuit C computing some Boolean function f mapping n bits to m bits can be very efficiently converted to a reversible one, and hence, I mean, they didn't say this in the 70s, but also hence a quantum one. Which looks like this. It's some, I'll call it QC for a quantum circuit, or maybe I should call it RC for reversible circuit. But it takes in n plus a bits, a for number of ancillas, and outputs m plus g bits. M is like the number of real outputs, and g is the number of garbage bits. And the number of input bits is the same as the number of output bits, so n plus a equals m plus g. And in what sense does this new quantum circuit compute? Sorry that I'm doing it way over here to finish this thought, but in what sense does it compute the function f? Well, in the sense that it does this mapping. Sorry, this is the last line of that theorem. Like, x followed by a bunch of zeros. This is n bits here. These are the ancillas. Maps to f of x. That's m bits. And then some garbage, where the garbage can depend on the input. Let me write it like this. Garbage of x. And that's g bits. Okay? And just a brief aside to say what does efficiently mean. Actually, there's two aspects to it. First of all, it means that, the quantum circuit is not much more inefficient in terms of number of gates than the original circuit. Basically, each gate in the original circuit gets blown up to 1 or maybe 2 gates if you do this NOT thing in the quantum circuit. And also, each gate might cost you like 1 ancilla bit. Or actually, I suppose 2 if you have a lot of these fan-outs. But basically, the number of gates plus the number of wires in the original circuit is proportional to the number of gates in the final circuit, and the number of ancillas at most. And actually, there's another aspect of efficient. It's not just that this new circuit is efficient, but also the algorithm that takes the description or the circuit diagram C and produces this circuit diagram is also extremely simple. I mean, you just have to do this. Okay, so everything about this transformation is very efficient. Okay, finally, I don't want to, again, dwell on this too much, but you might say, Oh, what about probabilistic computing? Well, no problem. Quantum circuits can handle that too. If you want to simulate flip gates, well, you don't use C-swaps for this. Instead, you do this. You take a 0 and an ancilla, you put it into a Hadamard gate, and then you measure it. And that's it. Right? Because at this state, it's plus, which is 1 over root 2, 0, plus 1 over root 2, 1. Okay, and then when you measure it, it's like 50-50, 0 or 1, classically. And then if you want to like move this measurement gate to the very end using this principle of deferred measurement that's on your homework, you can do that too. Okay, so the summary is this demonstrates that quantum computers are at least as powerful, maybe up to some very small like constant factor and efficiency loss, as classical computers. So great. So that's good. Now, later we're going to go on and show they're much more powerful in some cases, but this is a good baseline. Okay. Now I actually want to ask you a puzzle. So here's the puzzle. We just saw that any classical, this puzzle doesn't have anything to do with quantum, by the way. We just saw that every classical circuit and or not circuit, any classical computer chip, can be converted into a reversible one that does the same thing. So in my puzzle, there certainly exist classical circuits, efficient circuits, for the multiplication problem. All right, that like take as input 2 n-bit integers and output their 2 n-bit product. Definitely there's like a pretty simple circuit that does that. It's on every computer chip. Great. So there's some circuit that does this. Now let's just do this process and convert it to a reversible circuit that does the same multiplication. And now let's reverse it. I mean, all of these reversible circuits or gates have like a reverse operation. So great. Does this reverse circuit solve factoring efficiently?
You need to provide garbage bits.
Ah, you're very fast. Good. That's right. No, it does not immediately, obviously, solve factoring efficiently because of the garbage. So when we say that this reversible circuit computes it, it computes it in this like somewhat funny sense that like you put P and Q here and some 0 ancillas, and it will spit out P times Q and some garbage that depends on P and Q. So now if you have some number n, which is like the product of 2, or m, which is the product of 2 numbers, yeah, you can write m here, but you have to write something here to give into the reversal circuit. And if you somehow put in some bits here that lead you to zeros here, then you'll know that you've done it and you've found an input which multiplies to your target number m. But there could be like 100 garbage bits here or 1,000 garbage bits here, and then you have like a very challenging task of like figuring out which garbage bits here, when passed through this circuit, give you zeros. It's basically like the SAT problem, if you're familiar with that. So it does not give you an easy method of getting a factoring circuit. All right. In fact, on the subject of garbage, we really don't like garbage. So this is fine if like you're trying to compute some function and like it's the very last thing you're ever going to do in your life. Compute it, get your f of x, go home. But one thing that you sometimes do is like have subroutines. Like you build like a circuit that does some task, and then you're like, great, I'll put that in the bank, and it'll be like a subcomponent of like a bigger circuit or a bigger function I'm doing, and maybe I want to use it several times. And it gets annoying if that circuit produces garbage. And in the context of quantum computing, it not only gets annoying, but it actually like ruins things. So it's not easy for me to give you an example right now of why it ruins things. I will later, but just take my word for it for now that like, for the purpose of quantum computing, if you have a circuit that produces some garbage, it's very annoying and it cannot be used as a subroutine. Somehow the garbage prevents sometimes like this quantum interference from happening. Yeah?
Can you not use the garbage bits for future useful bits?
Well, not so easily because you don't really know their state. And right, like you can't, like in quantum computing, like you can't like throw them in the trash or like measure them. Like here's kind of this sort of illustrates the point. Like let's say you trying to like make a quantum computer that produced the plus state. It's not very sophisticated. We can do this with like, you know, initialize something to 0 and do a Hadamard. But let's say this is some kind of example I'm trying to illustrate here. You wanted to build a quantum computer that like generated this. And let's say you like did it, but like in a way that accidentally created some garbage, which could depend on the output that you were trying to make. So maybe like somehow you generated this 1 over root 2 0 0 plus 1 over root 2 1 1, the EPR state. And you're like, well, I got the first qubit to do the right thing, and you know somehow I made some garbage that's like a duplicate of the first qubit. It's not very good. Like if you just like, we talked about this before, like if you like throw the second qubit in the trash and you say, now I'm never going to touch it again, I threw it in the trash, but like I want to proceed as though I had computed this, it's not really right to ascribe this state to the first qubit. As we talked about before, the correct state to ascribe to the first qubit here is that thing you would get if you had measured. So like 50% 0, 50% 1. This quote-unquote mixed state that a probabilistic distribution of our quantum states that we talked about when we were talking about EPR paradoxes and stuff. So in some sense, like even if you had this garbage bit and you threw it in the trash, you somehow didn't get what you want. You got this instead of this. That's not like a super good explanation, but like it's an example of why it's kind of bad. Yeah.
Well, I mean, when you're trying to simulate the classic computation, you only care about 0 and 1s, right?
Yeah.
Which means that you can throw away everything else?
Yeah, so in the context of classical computing, it's fine. I mean, yeah, you only care about the answer, and like you can throw away the garbage bits, and it doesn't like affect the output bit. And if you're only using your quantum computer to like do classical computations reversibly, then it's the same. Like, I mean, basically, it's not really a quantum computer. Like, there's no superpositions or anything. So I can only illustrate why like garbage is quite bad in the context where you're actually doing something really quantum, where there's like entanglement and stuff. And like that ruins like all the cool quantum tricks that you can do with entanglement. And so I can't easily show that until I've like shown some cool things you can do with quantum computing, which will be in future lectures. Yeah.
So we could reuse the component as a subroutine using fresh ancillas, but we just need to store the garbage somewhere and not measure it. And so it will keep producing garbage and it will pile up the more we reuse the circuit.
It's more like if you're not, like, if you set up your computation, unfortunately I erased this, but like such that like the only thing you wanted to do was get like, measure that first qubit, like you have a quantum circuit, you measure that first qubit and it's giving you the answer, then it is fine if there's like garbage. I mean, if you prove that your circuit works and the first qubit when measured gives you the correct classical answer bit with high probability, then fine. But like, as you're, programming or coding, you're usually doing things modularly, and like you want to say like, oh, this part of the quantum computer like generates this state, which is in a superposition of like interesting things. And if you generate like a state in like a good and useful superposition, but like there's garbage tacked on, then it's kind of like you have not correctly gotten it into the superposition somehow for this reason. So I'll do an example in a future lecture that will make it more clear, but this is all to motivate you to like agree that like we should try to like tidy up our garbage if we can help it. which is what I will now tell you. Yeah.
Yeah, like for example, in the case that you described, you actually can measure the second bit in like plus minus basis to get the first bit correctly, or something like this. Like you can actually make some additional transformation and then measure your garbage.
Like if your goal for like why you wanted to get this was because then you wanted to measure it because you wanted to get a 50-50 classical bit, that's kind of the analog of like if you were like almost done when you got this and like the last step was just measure and you've completed your overall computation, then this would be fine because if you take this state with the garbage and measure the first qubit, you'll get 50-50, 0 or 1. But like if you got to this state because you're going to put it into some like new quantum subroutine that, you know, does something interesting if the state comes in like this, then it might not work correctly if you put, if this qubit is entangled with some garbage.
Yeah, that's kind of.
Okay. So luckily for all this discussion, there's a cool trick invented by our old friend Bennett, Charles Bennett, in the 80s. Well, he invented it in the context of reversible classical computation, just because, again, in classical computation it's not so bad, but there's still something a little bit philosophically unsatisfying about the existence of garbage when you're talking about reversible computation. Like, if it's really reversible, it's not supposed to like leak information about the input. It's supposed to be like a nice, perfect closed system, and so like the garbage is still even aesthetically unsatisfying there. Okay, so he invented this trick. Uncomputing garbage. Okay, so here's the trick. Say, you know, you have, I'll do it in the context of 1-bit output functions, but it works just fine for any number of output bits. Say you have this Boolean function, you convert it, compute it reversibly, or quantumly, whichever. Okay, so it looks like this. And then you got some ancillas. Okay, and then really I'm just going to package all the gates together into like one gigantic circuit, which I'll call, I don't know, P. Perhaps because it's a permutation. And then you get the output bit here, f of x, and then you have like these garbage bits that you don't especially care for. Well, okay, based on the title, there's a trick for somehow getting rid of them, and I will just tell you this trick. You kind of want to like copy the answer somewhere and then undo the garbage. So the first step is like that copy the answer somewhere. We kind of know the gate which is most similar to copying in this quantum or reversible world is the C0 gate. So you C0 the answer with a new bit. So you prepare a new bit, which I'll call the answer bit. You initialize it to 0, and you C0 like this. And this kind of saves the bit down here, right? I mean, if this is a 0, this stays a 0. If the output bit is a 1, you flip this thing, and this becomes a 1. This is f of x. And this actually doesn't change. And then you're like, hey, this is reversible. So I'll just plunk down the reverse. So you just take all these gates, do them in the reverse order with the inverse operation, P inverse, and that's it. You plunk them in. And so, you know, by definition, you get out x1, x2, down to xn, and then ancillas that are all zeros. And voila, you get an output which is very pleasant looking. You got the input back, you got the ancillas back, and you got the answer right here.
Is the answer entangled?
What's that?
Is the answer entangled with something?
No. I mean, you get this. Well,
I mean, it used to be entangled in the middle, right? So now what happens?
Yeah.
I think it's when we talked about it last time, we agreed that the answer is entangled with all the the inputs, right?
Okay, so yeah, you're saying is what entangled with what?
The f of x entangled with like x1 or x2 or something. Because in the middle, f of x, like the answer
Yeah.
bit is entangled with the first bit.
This bit
Yeah.
is entangled with wait,
answer bit.
this one.
After you do the C naught, right?
Yeah.
Yes. So then after you apply the reverse operation, this means answer bit could be entangled with some of the, or probably all of the input bits.
It should be all of them.
No, but the it's going to like the reverse operation is going to unentangle it. That's part of the problem.
It's going to unentangle all of the bits except the answer one.
No, including the answer one.
Okay, so why?
It's gonna unentangle the garbage from the answer, but it's gonna entangle all the inputs from the output to the output.
So
That's exactly the point of doing a quantum computation.
so let me clarify a little bit. We're actually mainly interested in the case where this is just a classical computation. Like a classical reversible computation. So what we're typically going to be imagining is that you'll actually be putting a superposition of states in here, which is going to be the cool move. But like these are all going to be like classical, C swaps and knots and whatever. Okay, and therefore like for each, basis state here of like classical, 0, 1, 1, 0, 1, 1, 0, whatever, this computation is going to be like a classical computation. And then there's not going to be a notion of like entanglement like within that. I'll make that clearer actually at the very end of this lecture. But for now, I mean, just think of like, let's analyze this if these are all like classical bits and these are like classical reversible computations. So in that sense, what I'm saying, what happens here is if the input state looks like this, x, and this is like n unentangled, zeros and ones. Okay, so if x looks like, 0, tensor 1, tensor 1, tensor 0, or whatever. And then you tensor it with 0, a many zeros. And then you tensor it with one more 0. If that comes in, then what comes out is x tensored with the a bits, tensor with the single bit f of x. Okay, and this whole story is like a classical story. This is what I want to certify. That if you do this trick, then on these like kind of quote unquote classical inputs, you get this kind of quote unquote classical outcome. And this works also, if you have like multiple output bits, then you have to introduce like a new answer bit for each of them and like C0 them in like one at a time. Does that make sense? So let me make one teeny tiny additional remark. This is basically a remark for later, but I just want to like notice what happens if you put in a 1 here. The whole point is you put in a 0 and you copy the answer, but I just want to remember what happens if you put in a 1 here. If the answer bit, or bits, if there's more than one, are initialized to, well, let's say they're m answer bits, and they're initialized to like y1, y2, ym. Okay, I'm talking about these ones here. So for whatever weird reason, instead of putting in 0 or all zeros, you put in a sequence of bits. Then the C0 convert it to basically this string y XORed with the answer. So let me simplify. Imagine there's just one output bit. I'm saying, okay, if you put in a 0, then what comes out is the answer. If you put in a 1 initially, then what comes out is 1 XOR the answer. In other words, the negation of the answer. And in general, like if you put in some arbitrary classical string here, you got out the XOR of the answer with what you put in. So I just say that so that I can say overall, what really happens more generally here is that if you put in a string y of length equal to the number of output bits, then this becomes more generally y XORed with the answer. Okay, let me just circle this. So I can make a little definition. This is how we really like to say a quantum computer computes a classical function. We'll make a definition that we'll use later in the course. So we'll say a quantum circuit and I'll use a different word just so it's clear, implements a classical Boolean function so it's using capital F everywhere. Change that. If it computes it like that. Okay, as in that garbage-free manner. And basically, whenever I talk about a quantum computer, like implementing or doing or simulating a quantum circuit, I want it to be doing it in this way, okay, because we really don't like garbage. And I told you this just to say that it's kind of without loss of generality. Okay, it maybe doubles, again, the number of gates you use because you have to put in all these reversals, but it's not a big deal. Okay, so not only can a quantum computer simulate any classical circuit, it can also do it in this like pretty garbage-free manner. Yeah?
What is... Oh, you're just saying that's the definition.
That's the definition.
Yeah.
And in fact, I even tend to write this star definition a little bit different. I prefer to like swap the ancilla part and the answer part. So it's really like x, you usually see it written like this, x and y and some zeros. These are the ancillas. This is an answer bit, so that's the input bit. Goes to x, y XORed with f of x, and zeros. And this is the way that like quantum circuits normally compute classical Boolean functions. And here you really see the like interesting thing with the ancillas, this piece. They're really just like this funny catalyst that like you have to stick them in there to like make the computation happen. But then at the end, they're just like hanging out just in the exact same state they were in initially. So they have to be there, but they, other than that, don't really play a role. So it's nice actually for modular programming because like you can actually reuse the ancilla bits. They're like exactly zeros like they were coming in. And it's almost like they're not there because they come in, they go out in the exact same state. So in fact, sometimes people get sloppy. I'll probably even do this and say like, oh, we have a quantum computer implementing a function f. It like does this map. X, y goes to x and y XOR with the answer. And really, in order to do this, it's got to have some ancilla bits here in the input and the output. But they basically never play a role. So you just kind of sometimes forget about them being there. Yep?
So are they like memory in a sense?
Yeah, they're kind of like a working space. They're kind of like, yeah.
Can you talk about like, I don't know, space complexity of a quantum circuit in terms of the ancillas?
Yeah, I mean, definitely it's a concern if you're, making a quantum computer to implement some classical functions, like how many ancillas do you need? It is kind of like, the working space or the scratch space or the memory. Mm-hmm.
So how is this still reversible? Because if f is like and, then haven't you lost information?
That's a great question. How is this still reversible?
You still have x, right?
Partly because you still have x. So yeah, in fact, if I give you this, even if f is very unreversible, like it doesn't even have to have the same number of inputs and outputs, it could be like many to one. If I give you this, you can recover this because, well, you know x. And once you know x, you kind of know f of x. And therefore, by XORing it in, you can recover y. Yep.
So isn't this circuit then also a zone inverse?
Yeah. Yep.
Yeah, so like, what is the reason for which you want to stick y instead of just zeros there? Because getting y XOR f of x just doesn't make sense.
Yeah. Most of the time you would just choose to stick zeros in there. But I mean, I wrote it this way so as to, for example, see that like, you know, it defines a reversible computation. For any like x and y you hear, you get something out here, even if you don't plug in zeros. That's one thing. And occasionally we'll actually use this to our advantage to know that like not only do you get x and f of x if you set y to be 0, but sometimes we'll use the fact that like, oh, if you set y to be 1, in the case of 1-bit output, you get negation of x. Okay, occasionally we'll actually remember and use that trick. Yep.
Couldn't you start composing this where like y was from a previous like module and like have different functions composed?
Yeah. So I'll just end by saying like the one power move that quantum computers have will be this. Like, as we'll see, you know, if you have like some classical circuit C, you know, you can build a quantum reversible circuit that does this, basically. But then the point will be that you can not just feed in classical x's and, you know, zeros here. So we're going to use the fact that you can do this, like Alex said. But you can feed in superpositions. And we're going to like have our quantum computers like build the superposition over all possible n-bit input strings x. And we'll feed it to this circuit. And we'll get out a superposition over all pairs x, c of x. So like the circuit, in the same amount of efficiency as it took to compute one version of c, it will compute all the answers simultaneously. But they're stored in a quantum state in a weird way, and it's not clear how you can extract useful stuff out of this weird superposition of question-answer pairs. So the tricks on what to do, well, that's the heart of quantum computing. Okay, see you on Thursday.